Hello. So today is the lecture 9 of Data Communications and Network 1. Okay. This is the chapter 4, Data Encoding. This is the last part 3. We will include analog data to digital signal and analog data to analog signal. Okay. This will be just a brief explanation on these topics. Okay. Now look at analog data to digital signal. This is basically the A to D conversion, okay? So you have like voice signal coming in and you want to send out digital voice, okay, through the digital telephone system, for example. You can see that you have the analog data coming in on the left, okay, for example, voice, and go to the digitizer, okay, and you get the digital data, okay. So this is analog. Okay, sorry. So you have digital data and then you modulate, okay, and you will get analog data, okay, or ASK. So in this picture is a combination of analog to digital and digital to analog, okay. So the first part, the digitizer is A to D conversion, and when you get digital signal or digital data, then in order to send through the, for example, the cellular phone system, okay, that is in the air, okay, through the medium which is the air, then you have to use a modulator or digital modulator which is digital signal, digital data to analog signal, okay. So you can see that even though in the first, the source is analog data and what you are actually sending is analog, again, the analog, okay, ASK, it doesn't look the same, okay. On the leftmost side you have it's just a waveform, okay, of the voice, but on the rightmost side this is the analog signal that you actually send through to the air. You can see that this is OK. Okay, so this picture is a combination of two methods. Now let's look at the part of the first part, the analog data to digital signal. Okay, we can convert analog data to digital signal by using pulse code modulation, okay, or PCM. This case, okay, we can sampling, okay, the analog signal first, and then you can get a series of pulses that are discrete in time but continuous in amplitude. Okay, after that you can quantize the PAM signal, okay, to approximate. You can use n bits to approximate the amplitude of each of the PAM pulse. So the first one, PAM, pulse amplitude modulation, is discrete in time but continuous in amplitude. Okay, so let's look at this. But PCM that you want to do is discrete in both time and amplitude, okay, and encoded into a stream of 0 and 1. Okay, let's look at this picture here, at the system here. You have analog signal coming in, then the PCM encoder, you sampling the analog signal, okay, so you get something like this. You get something like this, okay. This after the sampling, okay, so we call this PAM signal, pulse amplitude modulation. This is still continuous in value because you're just sampling, you just get the value at discrete time. Okay, and then you will quantize them. You quantize the PAM signal. You quantize by put it into a grid, okay, and then you will approximate the value, okay, to fit just the limited value that you want. For example, if you use 8 bits per symbol, 8 bits to represent one PAM pulse, you will have 256 levels, okay. So if your value is in between the levels, you will have to approximate them, okay, to be only at one of the 256 levels that you allow. So after you quantize, then you get a PCM signal, okay. Then you will encode into 0, 1, 1, 0, something like that, into digital data. So this is how you go from analog to digital, okay. When you fit them, you can do something like this. This is a detailed examples, okay. The left hand side, okay, the left the left-hand side of the y-axis is code number 0 to 15. In this case, we use 4 bits per symbol, so you have 16 levels, okay? And the right-hand side is the normalized magnitude from 0 to 16. The solid line is the waveform, okay? So you have the sample, okay? The t sub s is 1 over 2b, okay? Which is the sampling frequency. 1 over 2b is the bandwidth of this waveform, okay? So we look at PM value. The PM value is, if you read this, okay, the first is 1.1. This is the value on the right, you read it. So the first point that you sample, okay, is 1.1. 1.1 is the magnitude here. It's a little bit more than 1. The second one is 9.2, okay, if you can see. This is 9, okay, 9. So the second one is about 9.2 here, okay. The third one is the PM value is 15.2, okay. This one we read it from the magnitude on the right-hand side, so you will get this number. After you get this number, then you quantize to the code number, okay. What is the code number? The first one is, you see, the first is 1, okay, it's code to 1 because it's closer to the code number 1 than the code number 0, okay, because it's a little bit higher than the meter point, okay. The second is coded to 9, you can see, can you see? Because it's in that solid line of 9, okay, it's in this the solid line of 9, okay, is in that level, okay, so it's code word. Now you look on the left-hand side, so it's 9. The next one is 15, okay, because it's in this level, okay, in this code level of 15, okay, so you can read it like that, and then 10, and then 5, and then 2. And then after you have the code number, okay, then you will get the PCM code, okay, by each of the code number is represented by 4 bits in this case. So 1 is 10001, 9 is 1001, 15 is 1111, something like that, okay. So you get that PCM code and then you can send it. You can do digital modulation later, or if you send with so you can send, if you send through fiber optic, you may use ASK or OOK. If you want to send through the to the air, you may have to use FSK or PSK after this, okay? So this is already the digital data. So that A to D conversion, the next topic and the last topic for this chapter is analog data to analog signal, okay? In this case, we use for radio transmission and frequency division multiplexing. The amplitude modulation, or AM, okay, the carrier signal is modulated, okay, so that its amplitude varies with the changing amplitude of the baseband signal. So the modulated signal, the high frequency, okay, signal, change amplitude based on the baseband signal amplitude, okay. So the baseband signal becomes the envelope of the carrier. So if you look at this, you have the baseband signal is on the uppermost level, okay, that's the baseband signal. The carrier signal is on the carrier frequency, okay. We can call this carrier signal, okay, has one fixed frequency, okay, which is a high frequency that is suitable to transmit through the medium, okay. The modulated signal is like you change the amplitude of the carrier frequency. It still have the same frequency, but the amplitude of it is changing based on the modulating signal or the baseband signal, and it look like it's become the shape, it's become the envelope of the modulated signal, okay. So how do you do that? Okay, so in theory, you have a signal coming in, the analog signal coming in, you multiply by the oscillator of the signal, okay. that generated from an oscillator will have the frequency of FC, which is higher than the bandwidth of the incoming signal. When you multiply together, you get the signal like this, okay? So the baseband signal becomes the envelope of the carrier signal, and then that is called amplitude modulation signal, okay, or AM signal. What is the bandwidth? The bandwidth is just 2B, okay? So if B is the bandwidth of the baseband, then the bandwidth of the modulated signal is twice the bandwidth of the baseband, okay, and center at FC. For double sideband surface carrier, okay, this is the case. Transmission bandwidth is 2B, or B sub M is the bandwidth of the baseband signal, okay. This is the case for double sideband transmitted carrier. Double sideband transmitted carrier, okay. Sometimes we call this one DSPTC, double sideband transmitted carrier spectrum, okay. So you can see it's similar to what I have just shown you in the previous picture, okay. The bandwidth is twice that, the bandwidth of the baseband, okay. This is similar to this picture here, okay, but this is the more simplified one. The bandwidth is the same. There is a special case of the single sideband transmission, okay. In this case, we send only one sideband. Usually we send the lower sideband, and we do not send the carrier. So we will use only half of the bandwidth of the DSP-TC case, okay. So for the if you send double sideband, okay, if this is FC, double sideband, okay, you send like this, double sideband, okay. If you use single sideband, you will send something like this. This is single sideband, okay. So instead of using the whole big triangle, we send only half of them, okay, because the left hand side and the right hand side, the lower sideband, this is lower sideband, and this is upper sideband. The lower and the upper sideband, they are the mirror of each other, okay. So if you know one of these, you can just flip, okay, as a mirror, okay, and get the other side. It will look the same. It's symmetry at FC for real signal, okay. So if you send SSB, you will save the bandwidth. The next one is angle modulation. For angle modulation, the frequency modulation and the phase modulation are considered both angle modulation, okay. There are also angle modulation, which is not frequency, and phase modulation, but these two are the ones that people know about, the most. For FM, or frequency modulation, the frequency of the carrier signal is modulated to follow the amplitude of the baseband, okay. Everything follows the amplitude of the baseband. This one requires more bandwidth than AM, okay. So AM uses less bandwidth, but this one is better because it gives better signal quality, okay. Let's look at this one first. This is modulating signal, which is like, for example, voice signal or the audio signal, and the second graph is the carrier signal, or with the carrier frequency, okay, a fixed carrier frequency. This is from fluorescent, okay, and I got the picture from fluorescent. So the second one is like the carrier signal, okay, fixed carrier frequency, and then you can see that the FM signal changing the frequency based on the amplitude of the baseband. So when the amplitude of the baseband is high, then the frequency of FM signal is high. When the amplitude of the baseband is low, the frequency of the baseband is also low, okay. Can you see? It changed the number of circles, okay, that close together, and then and then go, it's like it's slower, faster, the circle is faster and the circle is slower, represent the high frequency and the low frequency. When you want to generate this, okay, you can do it by descend the amplitude, descend the baseband signal, okay, with this amplitude that you can see, this waveform coming into the voltage control oscillator or VCO. The VCO is the voltage control oscillator is the device that will give you the signal, okay, with the frequency based on the amplitude of the input signal. So if the amplitude of the input signal is low, the frequency coming out of VCO is also low. If it's high amplitude of the baseband signal coming in, then output is also high frequency, okay, and you can see that the output signal has a constant, okay, it's a constant amplitude, okay, changing only the frequency of the signal, okay. Now the bandwidth of the signal is just similar to the AM, but it's more than AM, okay. Instead of only 2B, that bandwidth of the FM is 2B multiplied by 1 plus beta, and beta is more than 0. So the bandwidth of the FM is always more than the bandwidth of the AM because beta is more than 0. Okay. Then we look at phase modulation. The phase modulation of is that the phase of the carrier signal is modulated to follow the amplitude of the baseband signal. Okay. This one again requires more bandwidth than AM. I will explain these two in details, okay, in another class, the principle of communication class, okay. So in this data communications and network 1 class, I will just go very briefly, okay, that both of the FM and PM signal can be represented as the angle modulation formula, okay, which is ST equal to A sub C, the amplitude of the carrier, which is constant, multiplied by cosine of 2 pi f sub ct plus phase, okay, phase t. This is the function of the time domain of the phase, okay. So now for PM, the phase is n sub p multiplied by mt. Mt is the baseband signal, and n sub p is the phase modulation index. For FM, okay, the differential, the derivative, okay, derivative of the phase, which is from when you differentiate the phase by dt, okay, is equal to n sub f multiplied by mt, when n sub f is the frequency modulation index. N sub p and n sub f are constants. Okay, so in this case, you can see that you have to dip the phase. Okay, so the baseband signal is multiplied by n sub f is the dip of the phase. Okay, so this is the difference between the phase FM and PM. Carsten's rule told me that the transmitted bandwidth is equal to 2 multiplied by beta plus 1 or 1 plus beta, okay, multiplied by B, and beta is more than 0, okay. Beta is equal to n sub p, which is the modulation index, the phase modulation index multiplied by a sub m, which is the max value of mt. Okay, this is for PM, okay, and for FM it's going to be n sub f times a sub m, which is the max amplitude of mt over 2 pi b. Okay, this is FM. So you can calculate both beta for PM and FM. Okay, so if the baseband is not 0 amplitude, okay, you always have beta more than 0. Okay, you have a beta equal to 0 only if the baseband is just a 0 level signal, okay, which is not the thing that we use in practical sense. Okay, this is the case of the PM. Okay, you can see that it's similar to the FM case. However, the phase, okay, the phase is changing with the amplitude of the signal. So you can see that the number of circle, okay, or the frequency it does not follow the amplitude of the baseband. Okay, if you compare with this picture, in this case, when the amplitude of the baseband is high, the number of circles is high. Okay, so this is frequency follow the amplitude of the baseband in the FM case, but for this, okay, the frequency does not follow the amplitude. Okay, only the phase follow the amplitude, so it's a little bit difficult to see. In this case, okay, you have to differentiate first. So the input signal, the analog signal coming in, you differentiate. You got the, and then you send the result of the dip, okay, to VCO, and then you get the modulated signal, the PM signal. Again, the bandwidth is the same as the FM, okay, but beta is a little bit different, okay, based on the formula that I just give you. So this is the end of chapter 4, and the next step will be chapter 5, error correcting code and error detection. Thank you.